supercomputing by API. So what I'm going to talk today about is, or I should start a step back, going back, looking at virtual laboratories. And these are things that have come out of the Nectar project, and it's, I guess, the software as a service layer on top of the infrastructure that scientists, researchers can come in. They have an environment where their data sets are there, the tools that they need are there, and that they're tailored for their specific domain. They don't need low-level skills necessary to start doing their work. So things like the All Sky Virtual Observatory for astronomy, Virtual Geophysics Laboratory, Genomics Virtual Laboratory, and there are many more. And this is a fairly general-purpose pattern. You might call it a science gateway, a science web app, whatever it might be. And in the case of the ones that are web apps, some are kind of HPC based natively, or they have a remote desktop component. The ones that are web apps kind of look much like any other web app. You have a web server, a database, perhaps, and then you have the actual worker infrastructure that processes the data, and this is for the asynchronous processing part of things. So this is where all the work happens, I guess. And the question comes in: at what point does this no longer scale? That your worker nodes can't keep up? You can't put enough cloud resources into your virtual laboratory for whatever reason, or you need specialized resources that aren't there. So let's connect it to a supercomputer, to a HPC cluster, to try and overcome that and combine these two kind of approaches. So supercomputers, as they're currently designed, are just a big stack of computers tied together, often on very fast networking, which is quite specialized and not necessarily available on public clouds. They might have specialized data sets located. They might have high-speed storage, GPUs, that kind of thing. So we would like to be able to move some of the workload that we have on the virtual laboratory, because perhaps it's taking too long or it doesn't have the right resources to do that work, and move it over to the supercomputer, do some work, and take it back again. As far as the user's concerned, they don't necessarily know they're using a supercomputer. So, yay, supercomputers. They're I guess, there's contention about where they're going to be in the world, or in the cloud kind of world, but we think there's room for two, and the question is integrating those in the most appropriate way. So the problem, of course, this isn't straightforward. HPC systems aren't the cloud, they're managed services, and they're all a little bit different and optimized for their particular environment. So they each have their own scheduler. The scheduler is a piece of software that decides where each job runs on the supercomputer. You have many users submitting jobs at the same time, and its job is to fairly allocate those. There are different vendors, open source, closed source. They all have slightly different interfaces and quirks. The OSs are different, almost always Linux, but as we know, there are many, many flavors and permutations of that. And of course, the software stacks. With HPC, the pattern is usually that the software is installed for you by the administrators. It's managed, it's optimized for that environment, and every computer that you go to might have slightly different versions. And you might be looking at hundreds, if not thousands, of applications installed on any given supercomputer. And there's variations between those. And the last part is the hardware itself. There's going to be differences in CPU architecture. As I said, they might have specialized InfiniBand networking, GPUs, specialized storage, whatever it might be. How do we smooth all this over? So the dream is that you can write a virtual laboratory, you can write a web app for doing science, and you can write that web app, sits in the cloud, and you can push your work to any supercomputer that you can get access to and get an allocation on. There's not any dependencies on any particular scheduler, on any particular hardware. And this might be unpopular opinion, but wouldn't it be nice if we had a RESTful API to drive everything by? Before I was trying to do these demos and I found out I didn't have proper SSH access. If you can do all via REST, it makes things quite straightforward. So I would love to tell you that I've solved all this today, but I have not. I do have a couple of things that I've discovered that take the sharp edges off and make the job of the developers and the authors of these applications just a little bit easier, and that's what I'm going to talk about today. So the two things, it runs the full gamut of all the tech conference cliches, APIs and containers. No talk would be complete without them. So let's do the API part first. What we'd like to achieve with this is a consistent interface across schedulers. I mentioned there are different vendors, different interfaces. We don't want to burden developers with the nitty-gritty details of that if we can help it. If we can provide a consistent interface to schedulers, let's go and do that. These applications aren't much good unless you can provide data. It might be just input parameter sets, or they might be hundreds of gigs, terabytes of reference data that you have to crunch through, and we want to manage that. We want to work across system boundaries. You might be within the university network, you might be somewhere completely different, you might have ports that aren't open to you. We want to have the flexibility around that. And HPC administrators, and I hope I'm not offending any who are obviously here in the audience today, are conservative about how they run their infrastructure. They're not going to let you install any old bit of software that you come to them with. Ideally, the HPC system stays the same, and we work around that. And finally, we want to have it flexible and not bound to any particular language. So Drama is the first API that I'm going to talk about. This came out of a standards-based process. And I'll show you a bit of code and what this is like. So this is one that's been around for a long time, 10, 15 years, I think. And this particular example is with the Python bindings. So we kick off a session, which is this part here. I can't highlight things very well. We have this job template. In this case, it's just a trivial job of echoing something. It's a great use of a supercomputer. And then we have a wall time. So this is the maximum time that the job can run for. We pass that template into our engine, kick that off, and then the bottom part here, we're polling for this to finish. So this is something that actually has to run on the cluster itself. You can't do this on my computer, so you have to already have access, accounts, SSH access. But once you're on there, you can be a little bit decoupled from whatever the scheduler happens to be. So I'm going to skip this demo in the interest of time, and maybe we can come back to it. So the first thing about Drama is that it tries to take an approach of getting the maximal feature set that's supported by all HPC schedulers. And that's not a lot, unfortunately. There are new schedulers, and keeping in mind this is 10, 15 years old, that'll have features that just aren't covered in Drama. And you can override that and pass things in directly, but then we've kind of defeated the purpose of things. So you only have this subset of features that the Drama is able to cover. The other problem with Drama, and I don't think the authors of the project would disagree with me on this, is that it's more or less a dead project. It's been around for 10 or 15 years. It relies on the vendors of the schedulers to write support, and especially in the case of the commercial ones, they may not have an imperative to improve interoperability, because then you go and churn and move to another product. So they've done a second version of Drama, and while the first version is widely supported, the second version at the moment has only been supported by one scheduler, and it's only been around for a few years. So it's had a good run. You can still use it. It's still very solid, but it's not perfect. So it has wide support. It's not particularly friendly. You're going to be looking at PDF spec sheets if you want to get this working. You have to be on the machine that you want to run things under. Limited feature support, and it's not developed much anymore. So that's Drama. The second API that I want to talk about is Saga. So this takes a more flexible approach. It's a newer project. It also came out of a kind of standards-based process. But if you look under the guts of it, there's an adapter-based infrastructure such that you can go and plug in whatever layer you want to connect to the particular schedule that you're dealing with. It's not bound tightly to a particular standard. So if I walk through this one, again, I'm using the Python bindings. You notice the first nice thing, I can actually do it over SSH. So I'll run the demo in the moment, and this will be on my local computer. We've got the definition of how you connect to this thing over SSH. Again, we've got a job template, much the same as before, kicking it off and waiting for it to happen. So cross your fingers. Give it, 10 seconds before we, quit? Oh, here we go. Job running. Job finished. Must have done something right in the past life. So that's one part of it, and I mentioned it can handle files as well. So this is the nice part as well. You've got that SSH connection. We'll use that to push our input files over to the supercomputer and then pull them back again, all within the same environment. So this is great. This is really handy. I've used this a bit. If you just want something simple, easy to use, Saga's pretty good. It has a nice level of kind of features. Doesn't support as many schedulers as Drama, but it's still pretty good. It's still not a web API. Maybe you don't care and you're happy to just work in Python or C or whatever it might be, and that's perfectly good. So the last API I want to talk about is Agave, and this is the API all the things approach. And when I mean all the things, I mean all the things. So we're talking about HPC and virtual laboratories today, but the scope of Agave is quite a bit larger than that, and it's basically the infrastructure that supports the Cyverse program out of the US, which supports a very wide range of science applications. So it does execution systems, both HPC and just plain VM instances that you happen to have access to. Storage systems, it'll monitor those systems like something like PagerDuty to make sure they're online. It'll handle metadata, permissions, history. It's all event-driven, and it's all driven via a RESTful API. So again, we'll try for 2, and we'll try playing with the Agave API. So I'm going to use the RESTful interface. That's the only thing, but I'm basically driving it via this little command line interface I give you. And all that's doing is doing curl things. So we have the notion of systems in Agave. It could be a storage or an execution system. In case you missed that, I'll go back up. We're just doing a get to this URL here. Say, tell me the systems, and we get a nice JSON payload back, listing all the execution systems that I've created, and you can go and post systems, and that post will have things like, it's at, I was warned about that, it's at this address, you connect to it using this authentication, it supports this scheduler, and it'll store that information, and you can go and talk to it. And here are the various details here. So I've got Spartan, which is our local HPC system at the University of Melbourne, but you can also just have a VM instance. It could be OpenStack, it could be on Amazon, it could be sitting on your desk, it doesn't really matter. So the next one I'll try is the idea of apps. Apps are just a bit of code you want to run. It could just be a shell script wrapper on a given execution system. So again, these are ones that I've created in advance, and all they're doing, much like all my demos, is just kicking off an arbitrary shell script. Again, if I go back to the details of that, again, it's just a nice self-explanatory API that I can use to pull this info out. And now let's go on and kick off a job. So we'll look at the payload for this. So again, it's just a bit of JSON that we're going to post to Agave, and then Agave will go off to the HPC system and run the job for us. So those are the inputs there. It's got a name and kind of the identity of that job. And again, see how we go. So this time we're posting rather than getting. And Spartan may or may not like me at this point. So it may not go through, and if it doesn't, we'll try doing it on a Nectar VM instead. I'm looking at Lev, the system administrator, to, as the gatekeeper of, Yeah, all right, I tried. So what I'll do instead, and this is the flexibility of it, right? You could have logic in your app to say, oh, it's a bit busy today. How about I go and just kick it over to a Nectar VM instead, and I've got the definition there for that. Oops. And hopefully I'll have a bit more luck with this one. There we go. So that's been submitted. And we have a whole bunch of other metadata and associated information about this job. We can now go poll this job. This application becomes a job, I should say, once it goes in. And you can go and see how it's going. It'll have various error states, as it kind of works through the process. So that's only today. On another day, it might be a bit different. So that's driving it via the command line interface, but what I want to get across is I'm just doing curl, right, to URLs and pushing JSON around. The power of this is a little bit more than that. So this is a demo application that the Agave authors put together called Agave to Go. And this is made in AngularJS. And I can go and have a look at jobs here. And hopefully the one that I just submitted has gone in here somewhere. And I can go and look at the systems and so forth. So this is, as I said, an AngularJS app, and the important thing to get across with this is that this is a purely front-end web application. You could take the JavaScript that composes this application and go and stick it in Dropbox, stick it in Swift, put it in S3. You don't need to run your own web host necessarily. You could build a science application that is just a bit of JavaScript And then it goes and shoots stuff off to HPC, shoots it off to a VM somewhere or a series of VMs, and does work for you. And that's it. You can all do it with REST. So I think that's pretty powerful. So that's Agave to go. The downsides and positives are kind of the same. It's hosted, so you are depending on someone else. At the moment, this is, as I mentioned, part of the Cyverse program in the US, and we're investigating standing our own version of it up in Australia. It's RESTful. Maybe you don't like that. That's okay. And it does everything, which may not be good for you. If you want to do something considerably simpler, Drama or Saga may meet your needs a hell of a lot better. So onto containers. Why am I talking about containers now, you might be asking? So this is a genomics application called bowtie. It's used for sequence assembly, so you get reads out of a sequencer and you're wanting to align them to a reference genome. And like all these applications, there are many versions of this. So we have the ones here installed on Spartan at the moment. These are on one of the massive machines at Monash, and these are the ones at NCI. The thing I want you to notice is that there's no consistent version across these three systems. Maybe you don't care, and that's fine. You want to take that gamble. But chances are you do, and for the sake of research reproducibility, you want to make sure that you are running your pipeline with exactly the same versions of software, whether it's running on your Nectar virtual laboratory or whether it's running on a HPC system here at Melbourne or in Canberra in the case of NCI. How do we deal with this? You can go and talk to our lovely system administrators, but they're very busy and highly stressed and underappreciated. And to the extent we can make their lives easier, we can investigate bringing our own software to manage that. And there'll be trade-offs with this, but it's something to think about. So this is where containers come in. Let's use containers on HPC, everyone. But no, you can't do that. So you need root access to run Docker, right? To run the Docker daemon to actually do this. And you will be laughed at if you go and suggest this. But there is a way around this, thankfully. So there's another container technology called Singularity, and this is really designed exactly for this application of being able to move scientific workflows from your laptop to a Nectar VM and to HPC, and not needing root to actually run that container. So in many ways, it's a simplified version of Docker. It's image-based. You just get a big fat file with an X3 file system. Has everything in it. It's not layered like Docker. The network access and hardware access is pretty flat. You don't tend to have to worry about ports. Everything just passes through. And you can expose mounts between the host and the container, much the same as what you do with Docker. So for those of you who haven't seen Singularity before, I'll just run quickly what it's kind of like to use. So you create a container, just a blank container, which is just a file system at that point with nothing in it. Go and bootstrap that with a base OS image, and there are other ways to do that. And then you can go and shell into this container, and I've got the little flag here, the -W, and that's the writable flag. When I do this, I can now go and mess around with this container, install software, bring my data sets into it, reference data sets that are read-only, whatever it might be, and then I exit out of that container, and it's now persisted within that container. The other way to do this is to use Docker. You can import Docker containers into Singularity. It doesn't always work perfectly. If there's run scripts and that kind of thing, you might have to tweak things a bit. But generally, you can take whatever images on Docker Hub, and there are, for instance, a lot of genomics images and so forth that are up there. Bring those in and use them on Singularity, and that's usually quite straightforward. And then you run it, and this is what it looks like when you run it. So we'll give a little demo of that. Because Spartan is kind of thrashed at the moment, I'm going to try again just on a generic Nectar VM. So I've got Singularity installed on this Nectar VM. You can also have it installed on Spartan. It's not on every supercomputer, but it's getting around. And call Singularity, and we're executing this bit of bash here. And this bit here to get across is that we're mapping the temp directory on the host to the jobs directory within the container. And I'll kick that off, and everything should be fine. So has anyone heard of digits before? doing deep learning stuff. So this is a web-based application for doing deep learning that NVIDIA produce. And this is the first kind of thing that I played around with because I was kind of laughed at when I said I wanted to run this on Spartan. And it does work. And importantly, it works with GPUs. So the GPUs actually get passed through to the container and it works fine. I can move that to other machines. There's a little bit of messing around with the drivers, unfortunately, but I'm told by NVIDIA that will get a bit simpler soon. So that's running it just on a VM. Typically run it as a HPC job. This is what a HPC job description looks like. If you haven't seen one before, it's a bash script with a little bit of special syntax up here to explain what resources that you want. We load in Singularity as the application we want to play with, and then we kick it off. And that's kind of all there is to it. It's just a couple of extra lines, and we can run whatever software we want within reason. It's not magic, is the thing I want to emphasize. There's still dependencies. We're sharing a kernel. You may or may not like that kernel. You may not like the hardware underlying it. People like Lev work very, very hard to optimize the software they install on HPC to take advantage of the particular architecture and environment that's been in, which means you may not get the speed that you otherwise expect. In the worst case, you may not get the outputs. So it's not going to be perfect. The other danger is that you can go and shell into one of these containers, work away at it for a few weeks, create this perfect, beautiful thing that does exactly what you want, and then you can share that. You can reproduce the same inputs and get the same outputs, but have no idea how you got there. And the beautiful thing about Docker and the kind of best practices enforce that everything should be in the Docker file and you know how you got from base image to whatever you're going to use. And so the same thing applies with Singularity, but it's a bit more DIY. So, conclusion, you can supercomputer enable your web app, and I'm hoping we can do this more. Unfortunately, you can't not be at least a little bit of an expert in how these systems work. You have to come along and talk to the administrators, understand the software stack and the architecture, and still be aware of it. But there are things out there that can take the sharp edges off and make life a little bit easier. We've got funding from Nectar. Thank you to Nectar to explore this area a little bit further. We're looking at standing up some demos, as I mentioned, with Agave. The one thing I mentioned as well is is around doing single sign-ons, so making the authentication flow between these web apps and HPC a bit smoother, and things like I'm doing now. So I found a lot of the virtual laboratories weren't necessarily aware of all the options that are out there, or what all the other virtual laboratories had already built. And so we're hoping to share that around both today, come talk to me, and we're looking at doing something at the OpenStack Summit in November as well. So that's it, I think. Thank you to all the VL managers and developers that helped me, the API developers, and Lev and Dan, who run our local HPC system at Melbourne Uni. Thanks very much.
Thanks, David. Any questions from anyone?
So when you did the submission to Spartan, so Spartan's full and so you don't get some immediate response. But of course, an HPC system, you would expect if it's full, the job gets put into the queue.
Well, it may well have.
So how would...
I think if I waited longer, it probably would.
Right. Okay.
But it can also get to the point that, the login node's also a little bit slow, and Agave itself being a hosted service, if they have a lot of jobs going through their queue, so that is a risk. You've added another layer and you're waiting both for Spartan and you're also waiting for the central service to do things. Right. So it's potentially at a cost. Usually it's pretty quick, but I did a live demo, so of course it wasn't going to work.
That was very brave and well done.
Any other questions for David?
Perhaps you mentioned, but perhaps I didn't get it. One of the things that complicates the matters in a distributed setting is connectivity. Configurations of firewalls, etc. Could you talk a little bit about that?
Yeah, and I was almost knocked over before I started this because I couldn't SSH out of the hotel Wi-Fi. It is a problem. So if you can get access to port 22 and do things over SSH, that usually works, but it's not guaranteed. And I think this is where something like Agave really comes into its own, because the web application developer itself they're just doing, HTTPS back and forth. Agave itself, as a central infrastructure provider, is the one that's actually kicking off jobs. And that's now a known and a constant. So if you were having problems, for instance, with a HPC administrator sees that this IP address over in the US is thrashing our system, isn't that bad? We can say, no, they're okay. They're a known application. They're managed. Here are the contacts. Please whitelist them and let them do things. So I think centralizing things to some extent with that kind of helps a bit.
We have time for one or two more questions from anyone. I've one question. I spent 10 years of my life trying to get grid computing to work. And I'm just wondering, how have things improved now? How have things fundamentally shifted to make the scenario you're outlining of transportable code, generic APIs, much more stable, much more usable now than, say, 5 or 10 years ago?
It's probably still quite fraught, is the answer. And I guess containers are the thing that everyone's excited about, that you have this generic infrastructure, but you still have this contention with multi-node jobs, GPUs, where you can't forget about the hardware and that. So I don't know the answer, unfortunately. I think it seems easier, and things like Agave are great to use, but if you can't get application developers to take them on board without pulling their hair out, or depending upon really large central organizations to maintain complex things over the long term, then I think you're still going to struggle.
All right, thank you again, David.
Thanks.